Welcome to this session in classification of effects. It's a really great pleasure to be the co-chair of this session. I am Ludovic Vaillant from CPN France. I'm a member of Committee 1 and the chair of Task Group 123 of ICRP, which is dealing with the classification of effects.
Good morning, everyone. My name is Michiya Sasaki from ICRP Japan. I'm a member of Task Group 123. Thank you for joining this session.
Thank you. The rapporteur of the session is Konstantinos Serides. He's also the technical secretary of Task Group 123. So thank you, Konstantinos, for your support and your help. And without waiting any further, I will call our first speaker. Frido Zolder is from the University of South Bohemia, Czech Republic. He's a member of Committee 4 and is a vice chair of Task Group 123. Frido, you have 15 minutes.
Thank you. Thank you very much to the organizers for giving me this opportunity to speak about Task Group 123, about the classification of harmful radiation-induced effects. All the members of the task group are co-authors of this paper. They all looked at the slides and they gave input, but you still have to keep in mind that this is what I took home from the first meetings of this task group. So it's a bit of a personal selection of things. We did discuss all these points that I put into my presentation, but no hard and firm decisions have been made yet. The task group has just started working. So we have to discuss these things and maybe other things that are not in this presentation, but have been brought up by members of the group or will be brought up today by you. Let me start with, so I'm supposed to cover some historical and conceptual aspects of the topic. And let me start with ICRP 103, the last general recommendations of the International Commission, and with the paragraph about the aims of the recommendations. The Commission's system of radiological protection aims primarily to protect human health. Its health objectives are relatively straightforward, namely to manage and control exposures to ionizing radiation so that deterministic effects are prevented and the risks of stochastic effects are reduced to the extent reasonably achievable. We have to keep this in mind as we discuss the two terms, and maybe it would be good to see how ICRP itself has defined these terms in the glossary of these recommendations from the year 2007. Deterministic effects are defined as effects due to injury in populations of cells, characterized by a threshold dose and an increase in the severity of the reaction as the dose is increased further. And they say here that these are also termed tissue reaction, which we will discuss later, the terminology. But here you see characterized by a threshold dose and an increase in the severity of the reaction. So these are the things that we think we can avoid by staying below the threshold and therefore prevent these effects completely. This is the idea. Stochastic effects of radiation are malignant disease and heritable effects for which the probability of an effect occurring, but not its severity, is regarded as a function of dose without threshold. And because this is so, it is assumed that already small doses with a small probability can induce these effects. Therefore, we can only manage these effects and can stay as low as reasonably achievable, but there's no possibility in this framework of thinking, no possibility of preventing the effect altogether. In the appendix, it also points out that these are effects resulting from damage in a single cell, which are called stochastic effects. So deterministic effects with the injury in populations and stochastic injury in single cells. Then in the chapter about biological aspects of radiological protection, the Commission refers back to the earlier general recommendations, publication 60 from 91. There, the Commission classified the radiation effects that result in tissue reactions as deterministic effects and used the term stochastic effects for radiation-induced cancer and heritable disease. Then they refer further back to 1984, publication 41. Effects caused by injury in populations of cells were called non-stochastic in that earlier publication, not deterministic, but just non-stochastic. And this was replaced then by the term deterministic, meaning causally determined by preceding events. They point out that there are two different kinds of terms here. One is the generic terms, deterministic and stochastic, and they acknowledge that these are not always familiar to those outside the field of radiological protection. For this and other reasons, they also use the directly descriptive terms, tissue reactions and cancer heritable effects, respectively. However, the Commission recognizes that the generic terms, deterministic and stochastic effects, have a firmly embedded use in its system of protection and will use the generic and directly descriptive terms synonymously according to context. So we have two kinds of effects. The linguistically pure terms are, or pair of terms are deterministic and stochastic, or descriptive terms, tissue reactions and cancer heritable effects. About the tissue reactions then in Annex A of these general recommendations from the year 2007, they say that an increasing number of studies on early tissue reactions have shown the ability to modify these using various cytokines and growth factors, primarily to stimulate regeneration of progenitor cells. Other biological response modifiers can be used for late reactions, in particular vascular modifying agents that delay the expression of organ damage induced in experimental animal systems. And here comes an important statement regarding the terminology, namely this ability to modify the response of tissues and organs means that the term deterministic effect is not entirely accurate, because quantitatively the effects are not necessarily predetermined. So once you go beyond a certain threshold, you can be quite sure that some effect will be there. So in that respect, it is determined that the effect is there, but quantitatively, because of these modifying influences of certain growth factors and so on, you can't be sure about the extent of the effect, about the severity of the effect, and therefore they say it's not entirely accurate to call them deterministic effect, because not all aspects are determined. Nevertheless, the term has become widely and firmly established, and the Commission continues to use the expression deterministic effects to denote tissue and organ reactions. That's in the annex. Then, of course, they also address the setting of dose limits for deterministic effects. They say in chapter 5 about dose limits, in the subchapter about dose limits, that in addition to the limits on effective dose, you remember effective dose is something reflecting stochastic effects, cancer induction in particular, but also to some minor extent hereditary effects. In addition to these limits on effective dose, limits were set in publication 60 for the length of the eye and localized areas of skin, because these tissues will not necessarily be protected against tissue reactions by the limit on effective dose. So we have to have additional limits for these deterministic, to prevent these deterministic effects. The relevant values were set out in terms of the equivalent dose, tissue or organ equivalent dose. These dose limits remain unchanged from 60 to 103. However, new data on the radiosensitivity of the eye with regard to visual impairment are expected in the year 2007. The Commission will consider these data and their possible significance for the equivalent dose limit for the lens of the eye when they become available. And they did that, and that led to publication 118, 5 years later, which is called an ICRP statement on tissue reactions and early and late effects of radiation in normal tissues and organs. And here they say this ICRP report has some changes to indicated threshold doses for tissue reactions compared with those stated in publication 103. First, the threshold dose for radiation-induced eye cataracts is now considered to be approximately 0.5 gray. It was before something like 2. For both acute and fractionated exposures, in line with various recent epidemiological studies. Second, circulatory disease has been recognized as an important late effect of radiation exposure, both for mortality and morbidity. An approximate threshold dose of 0.5 gray has been proposed for acute and fractionated or protracted exposures on the basis that this might lead to an incidence of the order of 1% of circulatory disease in exposed individuals. We'll come back in a later talk this morning to this 1% criteria. So where does the threshold really begin? Where do you define the threshold to be? And you define it where the incidence is 1% of 1%. So this is a bit of a historical, very few historical aspects, of course. There could be more quotes from earlier publications of the ICRP, but we have limited time. So I try to summarize what I have said or deduce from that certain questions that, as I said before, have been discussed in the task group but have not been answered by the task group yet. Does the current classification of radiation-induced health effects accurately reflect the best available scientific evidence? Very general. Is it really possible to unambiguously distinguish effects which are characterized by a threshold dose and those more appropriately described by the LNT model or by a linear quadratic non-threshold model? Can we safely assume that the former, namely those with threshold dose, are due to injury in populations of normal cells, while the latter result from damage in a single cell? And is it always the severity of the effect that is dose-dependent with population effects and the probability with single-cell effects? Or can both severity and probability be affected? In publication 118, in a few places, the Commission speaks about incidence and severity. So is that the same as probability or maybe not? So we have to be clear about these terms and decide what we are looking at. Should we take into consideration not only the dose dependence, the mechanism of action, the effect measures, but also what I briefly indicated, early and late effects or acute and chronic effects? Would that be another criterion to figure in? And then, of course, the million-dollar question, can the differences in all these aspects be captured in just 2 categories? Or is it necessary to have 3 or more categories? Which, of course, then leads us into another category of questions, more practical questions that I, as a member of C4, of course, I'm interested in the mechanisms and what C1 has to say about it, but from a perspective of C4, it's the application of the recommendations that is in the forefront. So what are the practical implications of a possible change in the classification of radiation-induced health effects? If we let go of this threshold versus non-threshold distinction, what would that mean for the general aim of radiological protection, which, as I told you, is to prevent deterministic effects, prevent one kind of effect and reduce the other kind of effect to the extent reasonably achievable. If we don't have two effects of this kind, how do we then define the aim? We would have to at least structure it, reword it. If the current classification is to be maintained, should we continue to use both generic terms, deterministic, stochastic, and descriptive terms, tissue reactions and cancer heritable effects, or to even mix them at times, as we do? We do speak about tissue reactions versus stochastic effects, which, as I said, is not linguistically pure, but practically it is done. And even we could discuss, would there be merit in returning to non-stochastic versus stochastic effects, because we don't think that deterministic is really a good, a precise and accurate description of what is happening. And finally, whether or not, and I have 7 seconds, whether or not the current classification is changed, we need to be clear about the criteria or the key considerations which allow us to distinguish between one category and the other or the others. And that is what you will hear about in the next talks. Thank you very much.
Thank you very much. We'd like to move on next speaker, Dr. Nori Nakamura from ICRP Japan. He is a biologist, as you know, and also he's a former member of Committee 1 of ICRP. So, please.
Bonjour, messieurs, mesdames. It's probably very provocative for you to hear my talk. I'm going to tell you that radiation carcinogenesis is not due to damaging single epithelial cells, but it's a tissue reaction. Okay. No, I have no conflict of interest. There are 3 reasons why I changed my mind. About 5 years ago, I was a believer of mutation theory of carcinogenesis. But then I got an idea. First thing is why relative risk decreases with the increase of time since exposure. Then I never heard good explanations for that. Second thing is why mouse survival curve shifts toward younger ages in parallel. And the third point is I carefully look at the past data, animal data, showing dose response increase of animals bearing tumors. But that was, I shouldn't say fake, but yeah, that was wrong. Okay, let's go one by one. Mathematically speaking, when cancer mortality increases with something like 5th power of the age, then shifting that curve toward younger ages, here by B years, then the relative risk is expressed as the ratio of the 2 curves. And that is expressed as here. That's a simple declining equation. So when the tau increases, then the relative risk decreases. It's a natural thing. But no one ever thought about that, to my opinion. Then I thought, okay, how about simply shifting the mortality curve toward the younger ages? Will it really fit the observed data? The left panel shows atomic bone survivors data and who are exposed to, say, 1 gray exposure. And the dotted line is not the fitted curve, just a simple parallel shift of the control curve. And when I saw that, I thought, oh, that's it. I didn't fit it, but it's exactly fit the data. How about mouse? On the right panel shows the same thing. Closed square is the observed mortality. But the dotted line, just a parallel shift of the control curve. Second thing is, when we think about the mutation causes cancer, and then the fraction of affected individuals increases with the increase of radiation dose, right? So that's why we see some kinds of dose response curve. However, if we think that way, we cannot explain the parallel shift of mouse survival curves shown on the left. Shown on the right is here it is assumed that 50% of the individuals are affected and they died earlier by cancer, and the next another 50% were not affected. Then in that case, survival curve starts to go down earlier than usual, but then at the end, same age, because half of the animals were not affected. But as I look back, excuse me. How can I come back? Oh, I'm sorry, I didn't, probably I missed some data. Past animal data shows mostly the survival curve shift toward the younger ages in parallel. The slope does not become shallower as indicated in the previous slide. The third point is the so-called cancer dose response. Left panel shows the mouse liver tumor, and the right middle panel is rat mammary tumors. And we see very nice dose response. And I was happy to see that. But after careful reading additional papers, then on the left side, this kind of BROC3 mice get spontaneous liver tumors in about 50% if those animals are kept until their natural death. The middle one, the SD rats get mammary tumors in about 70% if they are kept until their natural death. So my interpretation is on the right panel. Radiation causes shift of the onset age to younger ages. And if the observation is terminated prematurely, then we will get wrong conclusion. That's the point. And there are examples showing that when lifelong observation were made, then the proportion of mice dying by cancer or non-cancer does not increase. I'm amazed. It was 1965, more than half a century ago. But we didn't took that information carefully. And the right side panel shows that radiation exposure causes life shortening. That's very clear message. This is another recent result published by a group in Institute of Environmental Sciences in Japan. The study is extensive, 500 males, 500 females for each dose, they use different dose rate categories. And the left panel shows the male, right panel shows the females. And well, the problem of this strain is about 90% of the animals die by tumors. But anyhow, depending on the tissue, cancer in tissues, there is no sharp increase following chronic exposure to 8th grade, except for ovarian tumors in females. Well, that's a well-known fact that immature oocytes in mice are so sensitive to the killing effect of radiation. And that is a major reason, but it doesn't apply to humans because human immature oocytes are not that sensitive. So my story is after radiation exposure, previously we thought that epithelial cells are hit by radiation and the mutation caused cancer. That's the left side pathway. But in fact, radiation exposure damages the tissue and wound repair, tissue repair happens. And sometimes it goes, well, sometimes or often goes back to the normal stage. But during that time, cells or tissue require growth factor and other kinds of factors to do it more effectively. But that kind of factors are double-edged sword. So may go to normal repair, but also stimulate the either pre-existing or probably coming in the future, those say to be cancer cells may be stimulated. And I was impressed in recent studies by that NE, Natural Institute of Environmental Sciences group, that when they serially dissected animals, malignant lymphoma, 50% of the animals of this strain died by malignant lymphoma. But serial sacrifice did not show difference following radiation exposure, as shown on the left. But mortality, animals died by malignant lymphoma, was occurred earlier by about 100 days in the exposed group. When I say that, Nori, you know that radiation carcinogenesis occurs in the linear non-threshold type of dose response. Well, I say that is not all. There are exceptional cases, such as thymic lymphoma or ovarian tumor. Well, both are in rodents, but there are such kind of threshold type of cancer induction. There is such cases. So this is the last slide. In the past, we thought radiation causes hit single cell, and then that damage causes mutation and lead to cancer. But that would not explain the past animal data. So I now think the right side panel, it's a kind of tissue reaction. We still do not know what kind of tissue damage which lasts for, in the case of a human, all lifelong. What's the damage? We still biologically do not know it. But there are tissue, interactions among tissue cells. Okay, thank you. And this hypothesis applies only to those cancers which increases with the 4 or 5 power of the age, and such as childhood cancer or thyroid cancer with short latency period. Those are not the subjects to the study. Thank you very much for your attention.
Okay, thank you very much. The next speaker is Dr. Haruyuki Ogino. He is from Nuclear Radiation Authority in Japan. So please, you have the floor.
Thank you, Sasaki-san, and good morning, everyone. I am Haruyuki Ogino from Nuclear Regulation Authority. So first of all, thank you very much for giving me this opportunity, a wonderful session. So today, I am going to give a presentation on the dose response for tissue reactions with emphasis on the diseases of the circulatory system. So let's begin. My presentation consists of 4 parts: classification of health effects of radiation exposure, dose response for tissue reactions, radiation-induced subclinical damage and other risk factors and implications. As you know, in the ICRP system of RP, radiation health effects are grouped into 2 categories: stochastic effect, and tissue reaction. And classification is based on theoretical considerations of underlying mechanism. As you can see in this table, for stochastic effects, causative cellular damage is mutation, and the effect is thought to be originated from a single cell, as far as ICRP is concerned, and it is assumed that there is no threshold. On the other hand, for tissue reactions, cellular change is cell death or malfunction of the cells, and the effect appears only when the multiple cells are damaged, so there is a threshold dose. Diseases of the circulatory system, or DCS in short, is not attributed to a mutation of a single cell, so it is not a stochastic effect. If DCS is not a stochastic effect, it is a tissue reaction based on a dualistic effect classification, but the situation is not so straightforward. The risk of DCS increases with radiation dose, and according to recent epidemiological findings, the increase is observed even at doses lower than 1 gray, and the threshold is not clear. There is an ongoing debate on whether to include DCS in the determinant calculation. Then, a fundamental question arises. Does a small dose of radiation contribute to the risk increase in DCS? If the answer is yes to this question, how is it different from stochastic effects? And if the answer is no to this question, how much is the threshold dose? So it is just like a circular argument. And to explore these apparently paradoxical questions, I think we should get back to the basics. On what basis is the threshold determined? So this ICRP has used these schematic illustrations to explain the dose-response curve for tissue reactions. And this illustration first appeared in ICRP publication 60, and then publications 103 and 118. The upper graph shows the relationship between dose and severity. There are 3 lines in this graph, A, B, and C, and they represent different individuals with different radiation sensitivity. A represents the most sensitive individual, while C represents the most resistant, and B intermediate. And the lower graph shows the relationship between dose and frequency of tissue reaction in a population. So this is a dose-response curve. Dose-response curve starts to rise at the dose that induces sufficient amount of damage in individual A and steeply increases with the dose. And at the dose where the individual C exceeds the threshold for mobility, the dose-response curve reaches 100% of frequency. So what is the threshold dose? It is regarded as a dose below which the effect does not occur, but it is difficult to give a definition based on the absence of the effect. So practically, it is defined as the lowest dose at which the effect is detected, specifically ED1, estimated dose for 1% incidence. Regarding this ED1 for DCS, ICRP publication 118 describes that the definition of ED1 may be complicated by substantial baseline levels of specific tissue reactions or diseases that develop with aging in the absence of radiation exposure. For example, cataracts and circulatory diseases. Also, the publication 118 states that ED1 refers to effects just starting to rise above the baseline levels in unirradiated, age-matched individuals, and in the case of circulatory diseases, to a dose which would increase the already high natural incidence or mortality by only 1%. The description in the previous slide can be shown in these illustrations. The baseline incidence is not 0 for DCS. When the radiation dose reaches the threshold, the curve starts to rise. According to the definition, at the threshold dose ED1, the incidence of DCS increases by 1%. But this assumes that radiation-induced DCS has nothing to do with spontaneous lifestyle-related DCS. As we know, there are many risk factors for DCS, such as smoking, hypertension, and diabetes. In this formulation, it is implicitly assumed that radiation is independent of the influence of these risk factors. In other words, radiation has a different mechanism of action from other risk factors in inducing DCS. However, such a premises is questionable. It is well known that radiation causes oxidative stress. Risk factors for coronary heart disease are mostly associated with oxidative stress. And radiation-induced reactive oxygen species, or ROS, is suggested to promote lipoprotein oxidation and vascular inflammation. So circumstantial evidence suggests that radiation is likely to act jointly with other risk factors to promote atherosclerosis. Then what if a radiation-induced subclinical damage is added on that resulting from other risk factors? This was the start of our question. So now I go back to this graph again, in which the severity increases with dose. The severity is considered to reflect the amount of subclinical damage, and it can be interpreted as the relationship between dose D and the level of subclinical damage Z, as shown in the right panel. For simplicity, damage level Z is assumed to be proportional to the dose D, and the clinical symptoms appear if Z exceeds the threshold for mobility G0. Here I use the term damage as a subclinical change in an abstract sense, and its accumulation is assumed to result in DCS. And the variation in radiation sensitivity can be expressed by introducing a random variable x, and x represents the damage per unit dose for each individual, and its probability density function is denoted by fx. Then the incidence of the disease at dose D is given by the proportionate of those with Z exceeding Z0 in the population, and Z is the product of D and X. So the incidence is expressed by this formula. To examine the behavior of this model, a normal distribution has been assumed for random variable X. The parameters are set arbitrarily for illustrative purposes. The left panel shows the variation in damage level among individuals who were exposed to a certain dose. The area in gray represents those who develop the disease because they exceed the threshold, G0. The curve shifts right as the dose increases, and then the area in gray becomes larger. Consequently, this results in the typical sigmoid dose response curve shown in the right panel. As a next step, suppose that there are factors other than radiation and that they induce a level of damage represented by a constant y bar in any individual. If we assume that these factors act independently and additively to radiation, Z is expressed as dx plus y bar. The incidence is given by this formula. Under this assumption, the distribution of the damage level simply shifts right by y bar, as shown in the left graph. The dotted line shows the damage level with radiation exposure alone. No one exceeds the clinical threshold G0 in this figure, but most sensitive individuals reach the threshold as shown in the solid line when the contribution of other factors is added. This means that an exposure to smaller doses of radiation could cause the disease. Consequently, in the right panel, the dose response curve shifts left from the dotted line to the solid line. So then, what is it like if the damage from other factors varies among individuals? In this case, the damage levels becomes a random variable which is denoted by y with the probability density function of fy. If we assume independent and additive action, incidence of the disease at dose D is given by these formulae. To demonstrate the behavior of this model, hypothetical distributions are assumed again for illustrative purposes. Individuals are assumed to receive a dose of radiation much lower than the threshold Z0, just shown in the left panel, by the sharp normal distribution. For damage from other risk factors, a log normal distribution is assumed as there is a large variation, for example, in smoking and drinking habits. It is illustrated in the center panel. In this example, at the tail of the distribution, a small fraction of the population exceeds the threshold Z0 and develop the disease without radiation exposure. In other words, the baseline incidence is not 0. The right panel illustrates the distribution for the combination of radiation and other risk factors. Compared to the center panel, the peak shifts right and the distribution becomes wider, resulting in a large number of individuals to develop the disease. So this is the final result. The left panel shows the dose response curve for radiation exposure alone, and the right one, the combination of radiation and other risk factors. When combined with other risk factors, the dose response curve shifts left, and moreover, it is stretched out to the lower dose range, and the slope becomes shallower. What is shown here is just an example, but I should note that the threshold dose vanishes when a non-zero baseline is assumed. Okay, so far I have talked about the dose response for DCS, but it may be possible to broaden the scope. There are 3 underlying assumptions in our model. Accumulation of subclinical damage results in clinical symptoms. Damage is irreversible, and radiation acts additively with other factors to cause damage. These assumptions are not necessarily requirements for the phenomenon being proposed. I want to generalize the discussion with a slight modification. The first assumption is not changed, but the second one, instead of damage is irreversible, we can say that the damage is accumulative. And the third one, instead of additively, we can say that radiation acts jointly with other factors to cause damage. And looking at the rephrased assumptions, we find that the age-related diseases could meet these conditions. As a conclusion of my presentation, I'd like to summarize what are implied from this study. When a tissue reaction has risk factors that act jointly with radiation to induce subclinical damage, the threshold dose could be decreased depending on the extent of the joint effect. This phenomenon might be seen in age-related diseases that result from accumulation of subclinical damage. And finally, it is inferred that radiation accelerates the development of these age-related diseases in a dose-dependent manner. Thank you for your attention.
Thank you very much for a very clear presentation. Finally, our first speaker is Liz Hensbury from UKHSC. Liz is a member of Committee 1 and she's a vice chair of TG 123.
Thank you very much, Ludovic. It's a pleasure to be here presenting on behalf of TG123 and a pleasure to have listened to my co-presenters. I feel like I don't have a huge amount to say now other than just to outline what TG123 is hoping to do about all of these problems, but really interesting to hear your perspectives. Thank you. So as Frido said, the co-authors are members of TG123, so I present in this case on behalf of all of them. So thank you very much for the input and the fantastic discussions we've had so far. We already have seen this in this session and in previous sessions of the symposium so far, but just to reiterate, I think it's always useful to have the definitions in front of us. Tissue reactions are those which are formed by injury in populations of cells, characterised by the threshold with an increase of severity with dose. Deterministic effects, of course, also all still in use, whereas stochastic effects are those effects that result from damage in a single cell and in the current system of classification have no threshold, and then the frequency, but not severity, increases with dose. Thank you. So this is important because this forms the basis of classification. The classification forms the basis of the system of radiological protection. And I want to be very clear from a radiation protection perspective, these classifications are not supposed to represent all the complexities of all the different effects that we've heard some of today, but rather to be a pragmatic approach to capture the state of the art in terms of our scientific understanding and translate that into something pragmatic that we can use, something practical that we can use for radiation protection purposes. So the idea being that we manage, and as Frido has already said again, manage and control exposures to ionising radiation so that we prevent those harmful tissue reactions and reduce the risk of stochastic effects to an extent reasonably achievable. It's important as well. So this, as I said, underpins the implementation of the system in its current form. The problem is that there are some data, there are some old data and there are some new data that suggest that this might not be the best way to view the different types of things that radiation can do in terms of public health. So this slide represents what will probably be tens or even maybe hundreds of pages within the final report. So very, very brief summary of some of the challenges that may indicate it's time to revisit the classification. So for cataract, there's clear emerging evidence of stochastic mechanisms or stochastic-like mechanisms. For example, in terms of mutations based on DNA damage and misrepair, or evidence of transcriptional links with cancer formation, for example. Some types indeed might be best classified as stochastic and some as tissue reactions, depending on the level of dose and how that dose is delivered. So some really interesting data out there. It does seem that the dose response for cataract is probably linear, though, based on what we've got currently. We've already heard a lot about diseases of the circulatory system. We are continuing to gather evidence about what's happening here. Of course, diseases of the circulatory system are a number of different types of things, so stroke, ischemic heart disease, and vascular remodeling, all sorts of things. There is clear evidence of some risks at about a few hundred milligray, and as has nicely been outlined, the threshold might be somewhat lower than the 0.5 gray, which is currently proposed. For neurological diseases of the central nervous system, things like Alzheimer's as well, this is still relatively new in terms of the underpinning science, but there is some interesting growing evidence that low doses even might cause effects for exposures in utero or for children exposed. The mechanisms are things like related to neurogenesis and to changes in proliferation in cellular systems. So UNSCIR has just started looking at the central nervous system, so we will be working or watching very closely what UNSCIR are doing in terms of CNS effects. And then there's also evidence emerging on other effects, so in the immune system, for example, and that's very interesting because immune effects are linked to many of these other diseases also. So I suspect I don't need to tell the people in this room that several publications have said that we might need to revisit classification, and indeed as part of the overall review of the system of radiological protection, which is currently underway, seems like a very appropriate thing to do. So in response to this, TG123 has been initiated It's a joint task group between C1 and C4, the idea being that we look at the rationale. Frido has already nicely presented some of where what we have today comes from, but we need to really understand very clearly why we have the current classification and what those objectives are and how those two things are linked. Then also assess the current evidence and the reasons that might indicate that an evolution is needed. If it is the case, if we believe as task group and within wider ICRP colleagues that evolution is necessary, then we need to look at, one, what we might do as an alternative, and two, what it means. And this is really important. You know, I'll say on the next slide, we still want to prevent harmful tissue reactions and limit stochastic effects in their current format. But, you know, if we're thinking about classifying slightly differently, we probably won't change that overall protective aim. So lots of work for us to do. So the approach is to do some reviews of the literature, as you might not be surprised to hear, and we're specifically focusing on that challenging evidence. So in the light of the currently classified tissue reactions, DCS, cataract, CNS, and in utero effects, and then the stochastic effects of cancer and heritable effects. We'll also be looking at the different options around the evolution, and we've decided to adopt an options appraisal type approach. We're certainly going to need a lot of help with that. There are a lot of options that have been proposed, some already today. As I've already said, we don't want to change the fundamentals of protection within the system, and it really is important that we understand the implications of any changes. So this is not only from the sort of scientific and practical aspects, but in terms of tolerability and reasonableness and all of the other things that are so important to how our system works these days. So just to outline some of the things that we might consider, and I'm not going to go into a lot of detail, they've been covered in previous presentations, but some people are still using quite commonly stochastic versus non-stochastic effects. Maybe that could be good enough. Alternatively, we might look at severe versus other tissue reactions or short-term versus long-term health effects. But then perhaps, as with some of the evidence for cataract, some of these effects might be both. It's also been proposed that risk is classified by exposure scenario. Could be a very different way of looking at it, and then we'd have a lot of different classifications. And a key point here also is, as has been mentioned, how we deal with detriment. So currently we look at detriment only for the stochastic effects or the currently determined stochastic effects, but it's been proposed by one of our chairs, Ludovic, that we might look at disability adjusted loss of life years and life years living with disabilities. That's quite an interesting concept. And in addition, as was nicely presented in the previous presentation, that you know the long-term effects and in some cases the short-term effects, the relative contributions are still quite unclear. So we need to consider perhaps multifactorial causes of radiation effects. So we started the task group just about a year ago, something more. Time goes very quickly. We have met a few times online and once in person in July at RSN, and we have already defined our draft table of contents. So we know broadly the areas that we're looking at. We know what we need to consider in terms of the literature review and how we might move forward. And we have had some initial discussions on those potential alternative approaches, and then how we might choose what the best approach is for classification. But still, this is still a very early stage, still a lot to be thought about and discussed. To help us with this, we've heard a lot about mentees during the last few days. So we are recruiting some mentees as listed in the table here. And then the next steps will be really to dive in. We need to get into the literature and make sure we have a really good understanding of where we are with each of the effects. One of the things that will be really important, I've got a following slide on it, is the link with other task groups. So of course, as with all of the task groups of ICRP, TG123 does not work in isolation. So many of the important aspects of classification are linked with work of other task groups. And again, as with all of the other task groups, stakeholder input will be incredibly important. The last thing we want to do is propose something in terms of classification that doesn't work for the community. So we will be, again, as the other task groups, running workshops to ensure that we have stakeholder input in the development of this work. So I've just linked some of the other task groups to demonstrate to you that this is quite a challenging task. Lots of the other task groups are looking at things that are linked with what we're trying to do. So individual response, of course, reasonableness and tolerability, very closely linked with what we're trying to do, detriment and exposure situations, etc. So yes, lots of work to do in linking in with others as well as colleagues from the community. And then I think I'm just about in time. So hopefully I've made it clear to you, at least at this early stage, that classification of effects is very important. And, it is our job, it is the right thing that we now review this and think about whether it's the time to start doing something differently. This is not easy. I mean, nothing that ICRP does is easy, but I think we do have a particularly challenging task. Luckily, we've got great people on the committee. So we have experts in radiation protection from C1 and C4, but also colleagues with a great deal of expertise in the different types of radiation effects. So I think working together with the mentees and with other task groups, we probably have a good group of people to work on this. So we feel that things are going well, but we will need your help in bold. So absolutely, this is not done in isolation. We need to know what you think and how we can move forward based on the stakeholder needs. And then just to say thank you very much again for the opportunity to do this. Please do get in touch. We're looking forward to continuing the conversation with you. Thank you.
Thank you very much, Liz. And speaking about stakeholder engagement, we have more or less half an hour now for question, comments to our speakers. So the floor is yours.
So thank you very much for really a fascinating set of presentations. I'm Thomas Grant from Australia, and I'm working in oncology. I was delighted to see the immune system and the immune response occurring there, because that is currently really the big topic in oncology as immune therapies work and our colleagues in medical oncology become concerned that we as radiation people destroy their success. I think we really would need to include that. And as such, I thought it might be worthwhile to have also a colleague from the C3 to support that committee. More comment than a question.
Thank you very much.
So we have 4 lectures, and I have a lot of questions, but anyway, the first one is, so the first speaker said that the effect of this effect, the word effective dose, equivalent dose, and threshold. And so, do you have can you explain the clear definition of effective dose and effective dose and equivalent dose?
I think that would be a lecture in itself, but basically what I said, and I think what is important here is that equivalent dose reflects the action of different kinds of radiation in a tissue. So we have to consider the relative effectiveness of different kinds of radiation, which are summarized in certain quality factors.
Oh, excuse me. So in that case, so do you have some those even if it is not the dose effect, radiation effect, you should translate into the dose the risk. You should translate the risk estimation into the dose effect.
Yeah, this would be a long discussion, but basically even equivalent dose as it is defined because the quality factors or weighting factors usually for different kinds of radiation are again based mainly on stochastic effects on the cancer induction. So they are not appropriate to apply them really to tissue reactions. And the International Commission itself has recommended that maybe for some tissue actions, you rather apply relative biological effectiveness, but which one is then a question. So these are very hairy, hairy subjects, I think.
Can I have next question? Or
Please.
someone would like to?
Okay. Markus Eidemüller from BFS. And I have a question to Professor Nakamura. So thank you very much for your very interesting presentation. And I have a comment and a question.
Thank you.
So comment is, so we did ourselves a modeling study where we investigated different radiation mechanism on radiation acting on mutation, so initiation, but also then on promotion, clonal development, like the mechanism you proposed. And what is possible in a modeling study that you really can look at from each individual how cancer develops. And what we found that if you have a promotional mechanism by radiation, what happens indeed, as you presented, that you can have a cancer acceleration. And in fact, many more people can be affected by radiation than in a mutational mechanism. Not that the incidence goes higher, but cancer can just appear earlier. And this raises interesting questions about causation of cancer. Would you say cancer is caused by radiation if it's accelerated by 2 years? So this raises, well, interesting questions. And my question to you is now, what do you see as perspective to, let's say, for the development of biomarkers, if such effect might be possible to see in the future? And how it would affect the association between cancer and radiation?
I'm not very much enthusiastic, I should say, about the biomarker of radiation exposure, because radiation accelerates the natural cancers. So they go on the same way. So unique fingerprint or biomarker specifically for the radiation exposure, I'm sorry, I cannot answer to your question.
Okay, thank you.
Very interesting lecture. I'm sorry, I'm Yonekura from Osaka, Japan. Particularly for the 2 lectures by Nakamura and Omino-san. And I thought that maybe we could combine these 2 together. It's very similar, actually. And if you could combine together, we can have only one very simple model to explain the whole radiation effect. That's just my comment.
I was thinking the same way. So tissue I regret that we did not pay big attention to the events happening in normal tissue following radiation exposure. Only radiation oncologists are concerned not to expose the heart, for example, to over 20 gray or whatsoever. But following exposure to a few gray of radiation, we did not spend much time to understand what's really happened there. And one side, it goes to stimulation of cancer development. Other side, maybe some blood tissue may try to repair the damage, but sometimes repair goes well, sometimes not go well. And the point of non-cancer disease, I'm concerned because high blood pressure or lipidemia, or those kinds of diseases are, or somehow doctors provide medicine not to go too far, right? So to my understanding, the relative risk is of non-cancer death is 1/5 of that of cancer. But if the medical intervention had extended the occurrence of fatal events like heartbreak, then relative risk should be always lower in non-cancer type of diseases compared to cancer. So, well, I'm happy to hear your opinion.
Yes, please.
Sorry, take the opportunity to ask a couple of questions as well, if that's okay. So, Dr. Nakamura, thank you again. Very, very interesting presentation. Sorry, coming to you. So, following on from the question over here. Oh, not actually on. Sorry, is that better? Apologies. So, following on from the question over here, I was going to ask how your hypothesis fits with the sort of traditional model of not only radiation impacting sort of initiation in the kind of mutational form, but also then promotion towards cancer. And then also what the implications of your hypothesis would be for the system of classification. Does that actually change how we see cancer in the system? Thanks.
I mean, I had to answer two questions at the time. But what was the first one?
So traditionally or now?
Oh, okay. In terms of the relative risk or life shortening, well, at low doses, it's linearly related. So when the relative risk and life shortening, or at least in mice, I say, plotted, then it's a linear relationship. So, well, when we say below 100 millisievert, well, we cannot detect the effect. The same thing is true for the life shortening. That's okay? For the applications, I think important message is radiation-related cancer risks may be preventable. And that approach may also decrease the spontaneous cancer development. Well, I now hate the mutation theory because mutation cannot be reversed once it's happened. So, all in the past, we just sit and say, oh, that's happened. We cannot do anything. But that's probably wrong. We can intervene somehow to decrease the inflammation and then go beyond to reduce the spontaneous rate of cancer. Well, I really regret that if I could recognize this problem 30 years ago, I could be a radiation oncologist, not genetics. But I have no time left to me. So it's up to you, young people. Please.
So in order to study the risk, radiation risk, we have to separate the control term and the excess term. And most of the works related only the excess term, right? Excess risk. But so the control term depend on, for example, smoking or something like that. And how do you discriminate and move out that kind of things. Yeah. So third speakers, please.
Thank you very much for your comment or question. I think what you mentioned is the core of at least my talk, and maybe for our discussion in these sessions. And I think what is important is to consider the radiation as one of the risk factors, as I said, and it will not be possible to elucidate the relationship of all these risk factors and the incidence of disease. And it is quite complex and multidimensional, as you mentioned, because the background is totally different for each individuals. And we are just looking at the projection of this very complex curve to a simple plane, projected to a simple plane, which is dose and effect. And that shape could be changed by other risk factors. So, but at least we have to rely upon the epidemiological findings. And if that shows some linear approximation, and then we use that model. But if we can find another relationships, then we can use other functions. So I think what you mentioned is the core of what should we look at the effect of radiation in the context of the other risk factors. Thank you.
Okay, thanks you. Thanks for the nice presentation. But I just want to put the question to the panel. What is the real issue with using deterministic? Is it the threshold value, the dose at which effect starts, or what is the real issue, if I may ask, to everyone who can just answer?
I think indeed for practical radiation protection, it is the threshold value. Where is it, and how can we stay below it to prevent an effect? Is that really possible to prevent it? And then we come to the discussion of this 1% criterion, for instance. If we take it really to be 1% incidence, whatever the combined reasons are, then there may be some effects where we never can stay below that threshold. Or should we rather look at where 1% incidence is just caused by radiation? Can we really separate that? But the best we can do in such cases where we would have a combined effect would be to reduce the radiation to a level where we don't have a significant contribution of radiation to the whole effect. So, but how do we define that? Where do we define the threshold and the protection level? So these are again questions that will keep us busy for the next few years, I guess.
I personally felt when Fukushima disaster happened, I always ask myself, what would I have done if I were raising cattle there? And then annual dose is 20 millisievert. How much will it damage my life? Then official announcement is annual dose of 20 millisievert. That's the point. Over that, you should get out from that. But my calculation, if it is correct, is something like 2 weeks of life lost if I got cancer. Okay, I don't care about that. Staying in bed 2 weeks earlier or later, it doesn't affect my life. But that kind of information was not told to the public that time. So there are people who are afraid of 1 millisievert of exposure, and then left Fukushima and went to Tokyo, even south. So I think it's a very big mistake of ICRP. It did not say that, just formal explanation. That was really caused many people scared about small doses of radiation. Sorry, that's my answer to you.
We are having high natural radiation background area in Kerala, you may be knowing. There actually the annual dose, maybe people who are staying there, even at chest level, I have myself measured around 50 micro CO2 per hour. That is the dose rate. Means annually they must be getting more than 70 millisievert to 100 millisievert around. But there is no epidemiological studies, whatever have been done. The cancer rates are at par with any part of the country. So whether the dose threshold, what he was asking, whether it is 20 millisievert or 100 millisievert, what you are trying to tell us, whether can it be, I mean, whether it is conservatively it is been put at 100 millisievert, or can it be rethought to change it? Thank you.
I didn't quite understand the question. Just a comment. Or?
Yeah, you can. Do you have any comment? Whether you can answer, whether we can change this threshold dose from 100 millisievert to little higher.
So, what's the, sorry, it's whether the threshold, what is the threshold?
The threshold can be from the lower side to the higher side. That is what I was trying to ask you.
Well, threshold is defined, as Frida has said, as 1% incidence within the population based on the current weight of the scientific evidence that we have. And that, I think, whether we will change that is still an open question. So we're still reviewing the science. Does that answer the question?
Whether ICRP is thinking to review this, those threshold.
Yes. So within the task group, that is within the sort of terms of reference that we're looking at everything around classification of effects. So yes, that's certainly something that we will be looking at. Whether or not there's scientific evidence to suggest that an alternative definition is better, I feel that we're not in the position to answer that question currently.
Thank you again. Interesting discussion. A question, and I may have missed it. How much will radiation quality inform the classification of effects?
Yeah, as I indicated before, there is also a paragraph in publication 103 where it says that where should you use which weighting factors, and where should you not use weighting factors but rather relative biological effectiveness. So, and that is also again the dichotomy or the differentiation between deterministic and stochastic effects. And if we take away that distinction, then we don't know where to apply one and the other. So it is all combined, and this is part of the task of the task group to identify the implications when we change something up there. What will it mean down there, where we apply the weighting factors?
Yeah, this is very exciting. If you get a third class of effects, you may get a third quality factor. Yeah.
Definitely. Just to add to that, task group 118 is looking at RBE quality factor weighting as well. So, you know, as we've mentioned, we need to work very closely with the other task groups, including 118, to consider this. So, yes, everything is open.
the previous comment by our Indian colleagues, well, actually suggested a very important factor of dose rate effects. And ICRP has never considered seriously about that dose rate effects, particularly for the people who are living in a very high background area. That's a problem to accumulate, but maybe for a year dose, whatever. It's very dangerous. So I don't know, this task group is deal with this dose rate effect or not, but if someone should think about that. That's my comment.
Yeah, this is Gail Wallace-Jack. I'll just comment on that. TG91 is working on DDREF, dose rate effect. Now, it's been a long time I'm on that committee, but dose rate is certainly very important for that.
I'm a biologist, and I say we don't have enough information about the dose rate effects. And unfortunately, we had spent many years just trying to fitting the curve, alpha and beta. But that model is derived from the chromosome aberration data. And now I say radiation does not hit the tumor to be tumor cells, but just a tissue reaction. So we need more biological information at low dose rate exposure. Otherwise, it will never end. But it's a tedious job exposing with low dose rate for many hundred days of the animals. Well, we need money and stuff to do that.
Any other question? Go on, Liz.
Sorry, one more from me. So Haru, again, thank you very much. Really interesting presentation. I think, you know, from my personal perspective, not on behalf of ICRP, this idea that radiation accelerates effects that otherwise would be seen in with age anyway is quite an interesting one, quite compelling. Are there, and you presented sort of generalization in one of your previous slides, are there radiation effects that wouldn't fit that model though?
Yes, thank you very much. As I did my best to explain our model, it fits the diseases where the joint effect of radiation exists. So it means that for instance, like skin injuries, it's acute and very acute effects. And then in that case, the effect of radiation is a dominant factor, then our model does not apply. So, but our model could apply like a phenomenon where the effect of radiation act jointly with with other risk factors. And circulatory disease, it could be one of the examples.
Thank you. Liz, I see that you're interested in Haru's model. How would this fit with cataracts?
I think very well, yeah. Very well indeed, actually, yeah. So there's a lot of evidence in the radiobiological studies, at least, I feel, that does support this type of model. And actually, the paper that I referenced on the slides about longer-term effects, the UNESA paper, in fact, proposes exactly this, that there's a sort of level of cataract. The older you get, the more chance you have of getting a cataract anyway. And I've certainly seen it written that if you live long enough, you are going to get a cataract. Obviously, you know, there's sort of a lot of complexity within that. Yeah, the model that the sort of working hypothesis that we now have is that ionizing radiation indeed accelerates formation of cataracts that would otherwise be seen in old age. So yeah, it fits very nicely. Thank you.
Frido?
So it is clear that there are a number of effects that we don't understand enough, and we have new information like cataracts. We already have reduced also the not only our understanding of the threshold dose, but even the recommendations for the exposure of the eye. And for cardiovascular effects, it's clear that we have to do something about it, or we have to understand more for neuro effects or cognitive effects. Even there is a question, because in that classical drawing that you find everywhere, where it is about severe mental retardation, it seems clear that there is a threshold for the induction of severe mental retardation during fetal development, with radiation during fetal development. But when you look at IQ reduction, there's no threshold. You don't see a threshold. So you have two very closely related things, but with one you seem to see a clear threshold about 200 millisievert. With the other, you don't see anything. So what do we do with that? So there are these effects that we have to discuss, and that we have to either reclassify or first better understand and then think what it means. But don't forget that there are also things that don't go away so easily. So skin reactions, for instance, have clear threshold doses, and we don't have any indication that these were wrong. And so I guess that the recommendations for the annual dose limit for skin, for instance, will not be changed a lot, because it's just something that we have had for the last 80 years or 90 years. So at least as long as ICRP is in existence. And the other thing is, for the doses that we are talking about in occupational exposures, let's say 20 millisievert per year, or 50 maximum, or something like that, there's no change in the fact that there is a certain probability of having a cancer at a certain age, and that probability depends on dose. And it is not that each of us has 2 weeks shorter life, but it is some of us have a cancer and some of us don't have a cancer. Some of us get the cancer at an earlier age, maybe with radiation, some of us don't. So the average reduction in lifetime is 2 weeks, but it is still a matter of probability. What is the probability of you getting a cancer at a certain age with that kind of radiation? And then we have to compare that, for instance, for occupational exposure, we have to compare that risk of getting a cancer by occupational exposure with other occupational risks, for instance, accidents, which of course have a different timeline. And so there's again difficult discussions there. How do we compare that? But the fact doesn't go away that we are speaking about probabilities, at least at the doses here where our current occupational limits are. So yes, there will be changes, and there might be, we have to discuss these things and suggest maybe changes somewhere for some effects, but for some effects, the things that we have learned for the last 50 years will not go away. I don't think that there will be such a revolutionary change in the system. It will be changes here and there with some effects and some limits.
Okay, thank you very much. I think we have 2 minutes left. So thank you, Frido. Yeah. One last question? Okay.
Just one comment, the small comments from application side. I'm not a biologist, so, but my measure is the application of the ICRP principle and also those assessment to the emergency response and preparedness. And the very old publications like ICRP 40, the first principle is to avoid the deterministic effect. And the second is justification and optimization and dose limitation. It's very interesting, this discussion, and Nakamura Sensei said that the 20 millisievert is so low for in the point of the radiation effect. And I want to say that application of EPR we just focus on the very low dose, stochastic effect. The evacuation and sheltering and other protective action based on the dose below 100 millisievert. So that I think nowadays, and 100 millisievert is some numerical point that's only applied those kind of protective actions based on below 1 millisievert, 100 millisievert, and even to reduce a lot of optimization. So that's my thinking is this important theme is very related to our other fields and task group like tolerability and also justification. I'm involved in 2 task group, and so very interesting to this discussion. Based on this revision of the classification, maybe we have some advance to the principle or application of principle of ICRP to the real problems, I think. That's very important. That's my small comment from application side.
And this will be the final comment. Thank you very much. Before you leave, we have to thank a couple of people. I want to thank our speakers. I think it was really great to have you on board, and I guess we may have opened the Pandora box, but at the end of the day, we need to finish with something practicable. So thank you very much. And I want to thank also all the supporting organization because they're doing a great job since the beginning of the conference. So thank you very much to all the supporting people who are there. Thank you.